In the What is HDR course, we explored how the different HDR technology improves the quality of an image and introduced you to terminology like colour gamut and metadata to explain how this was done. This course will take a further dive into the implications of applying HDR when distributing video signals instead of simply sending them from a single source to a single display. To begin with, let's remind ourselves of the three methods that HDR can be implemented: HDR10, HDR10 Plus, and Dolby Vision. HDR10 and HDR10 Plus are commonly used today to increase the brightness levels of an image to 1000 nits and 4000 nits respectively. However, Dolby Vision is able to produce 10,000 nits, which is 10 times the amount of light than HDR10. It does this by encoding and hiding the dynamic metadata inside the image itself. This, though, creates some interesting challenges with video distribution. Let's start by seeing what happens if an HDR10 or HDR10 Plus signal is distributed to multiple displays. If the displays are both compatible with the stream being sent, then both displays will work fine, providing that the transport system maintains the metadata and delivers it to the displays. SDVoE does exactly this in Genlock mode. However, what happens if we have a mix of HDR10, HDR10 Plus and non-HDR displays? Well, the answer is that the HDR displays will work fine. However, the non-HDR displays will look extremely washed out and get some of the colours wrong. SDVoE is able to correct this using techniques to convert the HDR signal to a standard definition colour space, which the older display can understand. The older display may also need some scaling too, which again SDVoE is easily able to provide. Today, Dolby Vision is quickly becoming the most popular HDR format because of the higher performance it can theoretically offer. However, Dolby made some important decisions in the early days of HDR that pose specific challenges. Let's try to understand why with a bit of history. Back in 2014, Dolby Laboratories introduced the first Dolby Vision standard as a content mastering and delivery format similar to the HDR10 media profile. At that time, the main improvement over HDR10 was the capability to support dynamic metadata over existing HDMI links. Dolby Vision did not require a new HDMI standard, as it was embedding the metadata into the video signal. Knowing that current versions of HDMI would not pass the Dolby Vision dynamic metadata, Dolby developed a way to carry this dynamic metadata across HDMI interfaces as far back as version 1.4b. In other words, a Dolby Vision source was capable of encoding metadata into the pixel data values that the sync, or TV, was able to extract in order to perform the video processing required based on this reconstructed metadata. Of course, this mechanism was pushing significant complexity and processing requirements in the sync device. Moreover, it was also destroying AV synchronization between different TVs, because different TVs will produce different latencies or video delays to accomplish this intensive Dolby Vision task. Dolby Laboratories specified a new Dolby Vision mode of operation, low latency, referred to as LLDV or low latency Dolby Vision, as opposed to standard Dolby Vision, which is an older standard mode of operation for Dolby Vision itself. LLDV is the evolution of Dolby Vision, and this mode is now mandatory for all Dolby Vision devices, whereas the standard mode is no longer required. In short, with LLDV, the processing is done at the source eliminating all problems associated with the high latencies and the transfer of dynamic or static metadata, which is not sent to the sink in LLDV. In standard mode, the metadata is used by the display to tailor the video signal to match the display's specific capability for brightness. In LLDV mode, the display reports on its capabilities to the source via EDID, and the source customizes a signal for that particular TV. So, now that we understand a bit more about how LLDV works, let's see what happens when we start distributing it. Let's see what happens when two LLDV capable displays made by different manufacturers are in play. This means that the source will need to optimize its signal for one display or the other. And in this scenario, the source is provided with the EDID from display A. This means that display A will show an image that is the best possible image for that display. Display B can still show the content, and it will still be a very clear picture, even HDR. However, it won't necessarily be the best picture possible for display B. If display A is the higher brightness display of the two, then display B may end up with subtly washed out colours. If display B is higher brightness, then both displays will output a picture of similar quality, although display B could have done better if its own EDID was used. SDVoE technology fully supports LLDV, and over the past 2 years, all appliances claiming support for Dolby Vision are also supporting it. Furthermore, SDVoE is able to accommodate older displays which are not even 4K by using advanced processing to scale the original image and display it in the correct format. In this example, we see just that, a 1080p TV which needs to subscribe to the LLDV stream. By using the SDVoE fast switching mode, the image can be shown, and while it's never going to match the quality of the original source, once again, it's perfectly viewable. Compared to standard Dolby Vision, there's no more finicky data packing of metadata within the active picture pixel data, making LLDV much friendlier to distribute. Even a non-Dolby Vision capable TV receiving an LLDV signal will correctly display that LLDV signal. In the case of standard Dolby Vision, image corruption was the result we were previously plagued by. Latency is another huge improvement of LLDV, and AV synchronization between different TVs is now possible.